And welcome back. Right, so where are we? We introduced this basic idea of how we're going to use groups of neurons to represent things, and I mentioned that there's some software called Nengo. And what I want to do now is to start sort of doing some hands-on with Nengo, so we can actually get a little bit of a feel for how to make this work. If you want to follow along, again, if you have Python already installed in your computer, and if you're familiar with Python, all you have to do is pip install Nengo and pip install Nengo GUI. Pip install Nengo, that'll give you the core simulation system. Nengo GUI gives you the user interface that we'll be using. And then you can run that with the command Nengo. If you are not familiar with Python, you can still, I'd still recommend following along. Step 1, to install Python, I would recommend installing it via Anaconda. That you can get during that link. That Anaconda is just Python with a whole bunch of things pre-installed and sort of packaged nicely so it doesn't interact with anything else. And again, and from once you've installed Anaconda, you can go to the Anaconda command prompt and also do pip install Nengo GUI, and then that'll install everything. It'll download and install it all, and then you can run it with Nengo. And if you do that, it will pop up in your web browser, and it'll look something like this. So the way Nengo works is on the right-hand side of your screen is just a normal text editor. It's just a normal. You're just editing a file. You can use your own text editor if you have your own preferred text editor. But on the right is the actual program that is going to be defining the neural model that we're building. And then on the left, it's going to go ahead and visualize that. So let's, I'm going to start by starting with a totally new file. So I'm going to click up here. The default file shows up. I'm going to click here and I'm going to say, all right, let's call this example 1, just to give it a perfectly good name. All right, example 1 that file will be in whatever directory you were in when you started Nengo, when you typed Nengo to get it to open up. And that's this file over here. We're going to just go ahead and delete everything just to start fresh. Okay. So this is Python. If you're familiar with Python, great. If you're not, don't worry about it. Python's meant to be fairly minimal syntax where you can actually, at least the hope is with Python, you can make a pretty good guess about what's happening, even without much experience with it. The first line is always import Nengo. That basically just tells Python, hey, there's this extra package called Nengo that's been previously installed. Go and make sure you have access to it. And then what we're going to do is we're going to define a new model. And it is a Nengo network. Okay. So, all right. So that's so this is the first concept we're introducing, which is a network, and that's just a container to put some stuff in. At the moment, it has nothing in it, but it's just a container. It will have a bunch of components in it. You can have networks inside of networks. It's just an organizational tool. So I'm now going to say with model. This is a little bit weird, what's happening there. Basically what that's saying is everything that I put after this with statement, this is a bunch of stuff that's going to be automatically put inside that container. All right, I just didn't want to have to write model.add something. And so anything I define now will automatically be put inside that model. Okay, and that model is our container for storing what it is that we're building. Okay. Fine. Yes, Python is one of these languages where indentation matters. So you'll notice that after that with statement, I had a colon. And then we start the next line a little bit indented. Basically, everything that's indented, that's going to go inside this model. And the moment I stop indenting, that means I'm no longer shoving things inside our model. Okay. But things to keep in mind. Fortunately, the editor automatically indents, so that's all fine. Now, what do we want to do here? We want to define a group of neurons. So I'm going to make a group of neurons. I'm going to call it A. And the terminology in Nengo is that a group of neurons is an ensemble. So we could have said group, could have said pool, we could have said lots of other things. We're going to use the term ensemble, mostly as a reminder that these neurons are working together to represent something. Okay. There's a lot of different parameters we can define in our ensemble. The two ones that are always required is how many neurons are there. And we'll say there's 100 neurons. And then the other thing that's required is dimensions. So this is saying, hey, those 100 neurons, are they working together to represent one thing, or are they working together to represent two things? This can also be thought of as, well, what's the dimensionality of our input to a small neural network? Okay, so in this particular case, these 100 neurons are working together to represent one thing. Okay, when you do that, you will get, right when you finish that line, this pops up. This is going to be our representation of that group of 100 neurons. Okay, and that should just automatically appear. All right, so that's 100 neurons. So now what can we do with this? All right, so we have 100 neurons. I can move this around. I can also right-click on it, and I can generate some graphs. So for instance, one thing that I could generate is, let's look at the spikes. So I right-clicked and said spikes, and now I get this little graph. Okay, and if I now press play in the bottom right here, I get some activity coming out of these neurons. Okay, we're only showing 10 neurons at the moment here, and we can resize these graphs and things like that, but each of these rows, this is 10 neurons. If I right click on this graph, again, I can configure the number of neurons that we're going to be able to see. So number of neurons, I don't know, let's say we're going to show all 100 neurons. Let's play there. All right, there we go. So each of those rows is a different neuron. Great. They're just sitting there, having some background activity, firing away. You'll notice we don't have any input to the system yet. So there's Nengo is automatically. So why do these neurons have some sort of background activity? Well, what's happened when Nengo defined these ensembles is they said, all right, these neurons should have different properties. They should have different gains. They should have different, there should be different amounts of sensitivity to their input. Exactly the same variability that I was showing in that earlier video. And if I go to details and plots, we can actually see those. So this is the randomly generated tuning curves that it made. All it did is that for each neuron, it randomly generated some X value, so some value for which it would start firing, and randomly generated some maximum firing rate, and adjusted the neuron properties such that that'll work. And you'll notice that for a lot of these neurons, when they're not representing any input, or when the input is 0, there's still some activity. And again, that's often what one sees in different areas of the brain, and actual neurons. You'll have some background rate, and then neurons will fire faster or fire less quickly based on their input. And we're also seeing this thing where some of the neurons are responding to positive numbers, some of the neurons are responding more to negative numbers. And so that's just the defaults. All of these things are configurable, particularly if you have particular neural data that you're modeling and you have, the neuroscientists have measured some tuning curves. Cool, all right, we can go take that data and go ahead and configure that generation. Cool. Well, that lets us get some inputs. So what? Well, now let's say, all right, let's actually give an input to this system. Okay, so we have to find a group of neurons. Really, in order to actually show this we're doing anything interesting, we should have some input to the system. So I'm going to say there's some sort of stimulus. the stimulus is not neurons, so the stimulus is going to be something that's not neurons. Everything that's not a group of neurons in Nengo, we call a node. So a node is just input. It can be output. It can be a part of your model that you don't care about doing in neurons. You're just going to have it as just as arbitrary code. Anything that's not neurons. And the simplest sort of node is a node that just gives a constant value as an output. And so this is a node that just outputs a 0 all the time. Okay, so that's this thing here. It just outputs 0 all the time. Now we also need to make sure that this output goes into this. So now we need to introduce the next concept in Nengo, which is a connection. And we're going to go from the stimulus to A. All right, as you finish typing that, we now should see an arrow going between those. Now that we have that, again, we can press play and, all right, well, we're just feeding 0 into the neurons all the time. That doesn't help us much. But with the stimulus, I can right-click on that, and I can pull up a slider. And what the slider is going to let me do is change that input while the simulation is running. Okay. So if I now press play, and now I can move the slider around, and you can see that the neurons have different activity. Okay. Let me go back to showing only 10 neurons. So we can actually see, all right, so let's say take a look at this top row, that neuron there fires a fair bit for positive numbers, fires less and less and less and less, and eventually stops firing. And then there's some other ones in there that fire a lot with a big negative input, and less and less and less and less and less. Okay. Cool, so that's all fine. That's just, I mean, really all that's saying is, yes, we can make a simulation that has tuning curves that we've, fit what we desire. But really, staring at these spikes, it's really, if there's particular neural data I'm comparing to, maybe that's useful. But most of the time, I don't really care about what individual neurons are doing. If those neurons are working together to represent something, then I should really want to care about, well, what is it that they're representing? If I right-click on A and say value, what am I going to get here? Now what I've got, same graph at the top, same this thing here. Now I've got a single value coming out of these things. What is that value? I'm going to pause the simulation. Just some features of the Nengo interface. You've got this time slider across the bottom here. When you pause the simulation, you can actually go backwards in time and go see what was happening. So you can go ahead and drag that around. You can also change the width of the display by grabbing the side there. So you can go ahead and configure those graphs and look at things. And what we're seeing here is, as I was playing with that slider, there was this point in time where, oh, hey, look, I moved the slider, the neural activity changed. What this graph down here is doing is doing exactly what was happening in the video that I showed at near the end of the last part of this lecture, where, look, if these neurons are working together to represent something, then let's try to decode what those neurons as a whole are representing. And the particular sort of decoding that we're going to do is we're just going to say, let's take a weighted sum of these neurons. Okay, so again, this is the spikes coming out of the neurons. We also introduced the idea that each time there's a spike, it's actually releasing neurotransmitter, and then that's gradually being reabsorbed. So each of these spikes turns into a sort of the value jumps up and then decays back down again. For those in the engineering side, it is just a low-pass filter, where it's a exponential decay. It's another way of phrasing that. So we take these spikes, we put them through a simple low-pass filter that's supposed to sort of model what the synapse is doing, and then we do a weighted sum, and then the only free parameter in there is, well, what are the weights that we're going to put on, and being used to make this graph is Nengo has automatically gone and solved for, well, what are the best weights for just decoding out the original input from these groups of neurons. We could find different weights will go and compute different functions, but by default we can say, oh, okay, give me the weights that does the best job of recreating the input. And that's what's being used to generate this graph here. So what this is saying is this is the best job we could do. Given if I'm observing the activity of these neurons and I want to recover what information is encoded in there, this is the best job that I can do just by doing a linear decoding, just by doing a weighted sum of the outputs. You can do better than that with more complex ways of decoding information. There's lots of people that study optimal ways of decoding spiking or population spiking activity. We're going to restrict ourselves to doing linear decoding because we're pretty convinced that other neurons could maybe do that. I'm pretty convinced that neurons can do it, can compute weighted sums of their inputs. And so what I want to do is I want to say that this interpretation that we're showing here, this is how good other neurons could be at interpreting what's going on in this population. Okay? I don't want to assume some sort of really weird complex math to do a slightly better job of decoding information, because then I'd have to come up with some story about how it is that neurons could do that wacky math. But I'm pretty sure neurons can do weighted sums of their inputs, because that's what everybody sort of does with neurons. All right, so that's basically representing some things. I want to point out one interesting limitation to this, that ends up being relevant for lots of the things that will come up later. This stimulus slider here between -1 and 1, there's no reason we couldn't go farther than that. Like if I right-click on the stimulus slider and set its range and say, okay, it's now between -2 and 2, now I can make the slider go farther. That's going to cause more current to go into these neurons. It's going to cause some sort of activity to happen. And we're still going to be using some weighted sum. So what's it going to do? If I move my slider up, oh, okay, well, we're going outside of our graph. So let's right-click on our graph and set the range of our graph to -2 to 2. Okay, and now I'm going to go sliding up and down, sliding up and down. If I put the input at 2, oh, my output's only like 1.2. Whereas if I had the input at like some other number, I don't know, 0.5, then, it does a pretty good job of decoding out 0.5. So like in some range, it works perfectly well. Why is it failing now when I start going outside of the range of -1 to 1? What's special about -1 to 1? Okay, so it is doing a bad job of decoding at that range. That's because there's sort of whenever we have a group of neurons that's representing something, we not only need to know the dimensionality of that represent, how many numbers is it representing? This group of neurons is representing one thing. But we also need to know what sort of range that is. Is that between -1 and 1? Is it between -10 million and +10 million? Is it between -0.001 and +0.001? There's always going to be some sort of range. And if you get outside of that range, well, a couple things are going to happen. One thing is the neurons are just not going to be able to fire much faster. Okay, and you can sort of imagine that if I right-click on here, you can go back to this plot. Now, if I start extending this graph out farther to the right, the neurons just don't fire much faster. All right, it just flattens out. We don't have as much variability, so we can't do as good a job of decoding out, of seeing these sorts of fine-grained distinctions in there. Okay. But then the other aspect is that when we did that, or when Nengo automatically did that, find me the weights that does the best job of decoding out information, we also needed to implicitly say, well, when you're doing that optimization, what's the space that you're optimizing that over? And the default in Nengo is -1 to 1. If I want to change that, when I go ahead and define this group of neurons, I can also add in the parameter radius. And we're going to call it a radius because in general this is multidimensional. So I mean, we're looking at the one-dimensional case right now, but in general, they can be multidimensional, so we're just going to use radius. But now if we set it to 2, that's going to do two things. That's going to adjust the tuning curves of the neurons such that they're good at representing values between -1 and 1, or between -2 and 2. And it's going to do the optimization over that wider range. And so now when I go ahead and run this, now I do a perfectly good job of representing values between -2 and 2. Okay. All right. So that's a basic idea of using a group of neurons to represent a population code of a single value. I've mentioned a few times that this can generalize to multiple dimensions. So instead of half of the neurons firing more for a value of -1 and half the neurons firing more for a value of +1, the idea that we're going to do here is each neuron has some, if you say we're representing a two-dimensional space, we're representing two values. We can imagine that as sort of a two-dimensional space, an x and a y axis. And instead of some neurons liking -1 and some neurons liking +1, each neuron is going to have a randomly chosen direction in that two-dimensional space that it is most sensitive to. And everything else is going to be exactly the same. Okay. Why are we doing it this way? Because that seems to be what the brain is doing. Whenever we go and look in the brain about neurons that are sensitive to more than one thing, you tend to find this sort of preferred direction vector, preferred stimulus. Each neuron has a different preferred stimulus. The data that I'm showing right there is from the classic Georgopoulos experiments, where you have monkeys moving joysticks in different directions or memorizing different locations in a two-dimensional grid. And you look at the neural activity, and it looks like each neuron has some preferred direction, and their firing rate is higher the closer to that direction we're representing. So that just fits in with all the sorts of diagrams that we're doing totally fine. It's the -1 and +1 case is just sort of is just the one-dimensional equivalent of all of that. What do we need? So let's do that as an example. We go back to Nengo. I'm going to save the example that I just made here. There's the save button. I'm going to click over here, go on to example 2. And now what am I going to do? I am going to change the ensemble to being two-dimensional. Nengo is going to start yelling at me. We got this big sort of red error thing saying, whoa, something's gone wrong. There's a big error message down here. It's telling me something's wrong on this line here, that these do not match. And of course, they do not match. A is supposed to store two things. The stimulus has one thing in it. This is what it's supposed to do here. So what we're going to do is we're going to change the stimulus to be two things. And the way we do that in Nengo is we make this now a list of two items. Okay, so it's now a list with two items in it. So that's going to go in there. And now our stimulus is going to go across. Excellent. So now we have two sliders, one for each value. We have the same neurons. We have the same value graph. Oh, well, let's bring our radius back down to 1, just to be like that. I'm going to right-click on this and set its range to be -1 to 1. And now I'm going to press play. And now what have I got here? Again, I've just got this neural activity. If I go and change the slider, the neural activity changes. That's great. Oh, whoops, my sliders should also have a range of -1 to 1. Nope. So there we are. I'm going to feed in values. You can slide around, you can slide around. Okay, you'll notice if you look at the neural activity, each of these sliders affects each of those neurons. Each neuron is going to have some random sensitivity. Some neurons are going to be more sensitive to one than the other because it's going to be just randomly chosen. So you'll see that there's some neurons that are changing more with this one, and some neurons that are changing more with this one. But each one is going to just sort of have a randomly chosen sensitivity to those two. And then this graph down here is now showing two lines. And all we're doing there, all Nengo's doing there, is it's taking this neural activity, it's doing the same solving, and it's saying, okay, there's going to be one set of weights that does a really good job of decoding out one of those values, and there's going to be another set of weights that's going to do a good job of decoding out the other value. So they're both just different weighted sums for those outputs. We're just taking weighted sums of the spikes to produce these two graphs. Okay. So again, that's the information that could be pulled out. Okay. And you can notice some interesting little effects here. So if I go ahead and vary this one, the blue line does not change much at all. Okay. You will notice, there's a couple different things we can look at here. So one, that the fact that it's jittery up and down like that, that's just a consequence of the fact that we have spiking activity encoding it. It's being added up, it's just a sum of a bunch of spikes. If we increase the number of neurons, that should become less jittery. Here we are. All right, so you're seeing that should be a little bit less jittery now. If we drastically reduce the number of neurons, it should become more jittery. There we are. All right. So that's the sort of behavior that we're kind of expecting there. But we also get a couple interesting, or one other interesting effect that I just want to highlight here is fine. If I vary this one, the green line doesn't change much. If I vary the green line, the blue line doesn't change much. If I put the green line up here, the blue line up here, and then I vary this line, now the blue line's changing a lot. So this is saying that these neurons are not independently representing these two values. Like, so there's some sort of interaction happening here. And why is that happening? So why is it that our decoding is less accurate for some reason? When I've got a 1 being represented in one of these values, whereas if I had a 0 being represented, now it's much more accurate. This is another side effect of the radius aspect that I talked about earlier, right? That we're optimized over some range. If I try to get my neural system to represent the value 1, 1, this group of neurons represent 1, 1, that's outside of the range that it was optimized for. If it was optimized to represent values of a circle of radius 1, the point 1, 1 is outside of the circle of radius 1. We can also see that if I right click on A and I say an XY value plot. Okay, that's the same data as in, so these two plots have the same data. We're just plotting them in a different way. But now you can sort of see, oops, there we go. So there we are. So you can see the value going around there. It's just being plotted in a different way. If I put this out at 1, or sorry, if I put this at 0, and I go ahead and vary this, all right, everything's fine. I go ahead and put things out at 1. Now I go vary this. Oh, see that little curve there, what's happening? So this is the same thing as what we were seeing in the one-dimensional case where I tried to represent a value that was, say, a value of 2, but it ended up representing 1.2. If I try to represent values outside of the range it was optimized for, it will end up representing a value that's a little bit closer in. Okay. This, if I wanted to fix that, one way I could fix it is by just changing the radius. So I go and increase the radius. And now, whoops, and now we're doing a pretty good job of representing those points. Okay. And that all works fine. Okay. So basically, the reason I'm highlighting that stuff is I always want to be, it's not like It's not like normal math or floating point numbers in computers where it's just any number at all. Neurons are going to be good whenever they're representing something. They're good at representing something within a range. Okay, and we always and I often find that that ends up being important when we're building these systems. Okay. All right, save that. Let's go back. Where are we? That basic principle is going to extend to 3 dimensions, 4 dimensions, 5 dimensions. The largest I've done things is 512 dimensions. But that basic principle is going to hold. Okay. Cool. I can have groups of neurons. I can have them go ahead. Oh, actually, I should do one more example, I think, before getting into this. Nah, we're good. We'll be fine. Okay. So that's the general principle of we can have neurons represent things. And now the simplest thing I want to do past that is I want neurons to pass information from one place to another. Okay. Because I want to be able to build up larger, fine, if I know what individual group of neurons can do, but if I want to implement complex cognitive algorithms, that's going to involve like many steps, and so I need to be able to build up larger systems out of this. So if we sort of just think of this as from a programming perspective, engineering perspective, it's kind of straightforward what we're going to do here. This first component that I show over here, this x, so if I have some value x, I feed it into a group of neurons, and then from that group of neurons I can decode something out. The particular example we've just seen is trying to just decode out what the input was. And then if I wanted to then go feed that into another group of neurons, well fine, I can take that value, feed it into another group of neurons, and decode back out, right? It's just, we just do the same thing over again. There's nothing weird there. All right, so as a programmer, that makes perfect sense. If I go and talk to a neuroscientist, though, hold on a second. Whoa. There's nothing like that happening in the brain, right? Like this Y thing in the middle here, that does not exist. Okay, this group of, maybe if we might have groups of neurons and another group, 2 groups of neurons, and they might have connections between them. But those connections are between the neurons. They're not to some magical like Y value, component that then goes and connects to all the other neurons. That doesn't exist. Okay, the closest thing that does exist would be something like, oh, there's a whole bunch of connection weights from all the neurons in A to all the neurons in B, or some sparse connection, or there's some constraints on that. There'd be connections from A to B, but biology does not have this intermediate component. So how, if we want to map this onto biology, if we want all the components in our model to map onto biology, how can we get rid of that? And the answer to that question ends up being a little bit of somewhat magical math, and it sort of ends up taking advantage of the fact that we have decided to do this linear weighting thing. The fact that the only thing that this D thing is doing is some sort of linear weighted sum. And I sort of mentioned that's a thing that neurons might be able to do. And this E, that is also doing, it's the thing that's projecting Y back into these neurons, so giving each neuron a different preferred stimulus. That's also just a big connection weight matrix. And this Y value is also not particularly doing anything. It's just a value. And so that means that I could take this weight matrix D and this weight matrix E and just multiply them together. And mathematically, those things are identical, right? There's no difference at all in terms of the math, in terms of the simulation, in terms of what's actually going to be happening at B. So these two things must perform exactly the same way, okay? And so our idea is here that we can sort of postulate this Y thing when we're building our model, when we're constructing our model, and we're imagining what sorts of things we're putting together our algorithm in order to build up our large neural model. But when we actually want to compare it to biology, what's actually happening biology-wise is this weight matrix. we can then also put constraints on that weight matrix to make it sparse and have all sorts of all the other properties that one would expect to make that more biologically realistic. But for now, we'll just start with this one step of, look, if you multiply those together, you get a weight matrix. And this is a really weird way of generating a weight matrix, right? Like most neural network approaches, you do some sort of learning method in order to generate a weight matrix. You can sort of imagine that what we're doing when we solve for this D, we are doing an optimization process. We could do a learning method for that. But we're doing is a sort of a smaller learning problem that we then combine with this E that we've either randomly generated or we've generated to match biology. And those two things together give us a connection weight matrix. Okay. So if we do that, we end up with things like this. So this is this first part of this video is exactly what we saw before, where I take a sine wave input, feed it into a group of neurons, and then down here I'm showing, up here is the neural activity. Down here at the bottom is the decoded value. So this is taking the spikes, do the weighted sum of the spikes, and plot that. And then we're doing exactly the same thing here in B. We've got spikes, and we're doing some sort of decoded optimization, decode the spikes in order to produce the graph down here. But the connection weights between A and B are generated using the methods that I showed before, which is just, you figure out the decoder from A, you take the same decoder that you used in order to generate this graph, and you take the encoders for B, the thing that's making sure that each of those neurons has different sensitivities to different inputs, and you multiply those together and you get a connection weight matrix, and that's what's being used here. An important neat feature about this, so first of all, it works. We are passing information from the input to the A to the B. Okay. You will note that the neural activity is not the same between A and B. There's nothing in what I said there that means A and B have to have exactly the same tuning curves or exactly the same neurons. Indeed, they don't even have to have the same numbers of neurons. Right? So if you go ahead and look at the spiking activity up here, the spiking activity is different, but it still encodes the same information. Right? Because we can still decode out that same information from that spiking activity. And it's also important to note that when we do that optimization to find those connection weights, we don't have to consider the whole system. All of those optimizations are just local things that just have to do with that one group of neurons. This is what's going to let us scale up to really large systems, is that we don't ever need to do this sort of giant optimization across the whole system. We're just doing these local optimizations of, given the tuning curves of these neurons, what would be the best way of decoding it? And then you can think of what this, when we're solving for the connection weights from A to B, what we're doing is we're saying, okay, find me the connection weights that would do a good job of making sure B has the tuning curves that I want it to have. It's another way of thinking of what's going on here. Okay, it's a little weird. To add one more weirdness on this, it's important to note that when we do this optimization for A to B, when we do the optimization of, okay, given the spiking activity in A, let's decode some value out of it, there's nothing that says we have to decode out the identity function. We could do any sort of function. So for instance, we could say, all right, let's decode out x squared. Okay. Exactly the same setup I just showed. The only thing that I'm changing is when we solve for the connection weights between A and B, we find the decoder that will decode out from A the square of the value in A. This is very surprising. This is weird. Let's go through this as an actual example just to see what's going on here. Okay, I've made sure I've saved this. I'm going to go to example 3. Let's start fresh. I'm going to have a stimulus that is a node that has nothing in it, or that always outputs the value 0. And I have a group of neurons A. It's 100 neurons. It's one-dimensional. B, 100 neurons, also one-dimensional. Okay, we'll make a connection from stimulus to A. And I'm going to make a connection from stimulus to B, or nope, not from stimulus to B, from A to B. And then we get a nice little arrow. Get some spikes. Get some spikes. And a value plot. And a value plot. Okay, and run that model. And oops. No, that's not supposed to happen. I'm going to save this. I'm going to hit reload because for some reason the slider was not doing anything. I'm going to hit reload and remove all of these graphs. That's kind of embarrassing when Nengo does not do quite what I wanted it to do because it's my fault. There we are. Let's try this again. B spikes. Spikes. Try running this. Yay, all right, now we're happy. Okay, so we have, this is exactly the same thing I was just showing. The information is being passed from the stimulus to A to B. The neural activity, if I hit pause and go back here, all right, like the neural activity that represents a particular value is different for each of these groups of neurons because there's different, each neuron has a different randomly generated tuning curve. But we found a connection weight matrix between A and B that does a good job of passing information from A to B. Of course, if we go ahead and muck with the numbers of neurons, we can change how accurate this is going to be. So if I say only have 10 neurons, right here, B still does a reasonably good job. But of course, the neural activities will be very different because there's 10 neurons versus 100 neurons. And there's lots of fun stuff we can do, which say just sort of, okay, given a number of neurons, how accurate is it going to be? And if we change other neuron properties like firing rates and things like that, that's also going to affect all this. But the important, a big important thing out of all of this, if I just save this, is when we connect A to B, by default, it found the connection weights between A and B that would do the best job of passing the identity function, of just passing whatever the input was from A to B. But we can change that. I can define a new function. There we go. That's squaring. Right. And just when I make this connection, I can say, well, the function is this one. Okay, let's give it a better name. Let's say square. Square. There we go. Okay, so this can be any code you feel like. Right? It could be 400 lines of code doing some sort of really weird math. All that's going to happen is Nengo is just going to take that function and do the best, find the connection weights that does the best job possible of approximating that function. Okay. And if I now do that, well, if I go ahead and put the input at 1, I get a 1 out. Put it at -1, I get a 1 out. Put it at, I don't know, 0.5. I should get something around 0.25. We get that. All right. It's going ahead and computing some sort of, it's computing the function that I asked it for. Okay. It's not going to be perfect. All right. So, because it's just trying to find the best job that neurons with these properties can do to approximate that function. So, for example, what about this function? If x is less than 0, return -1, else return 1. Right? It's no longer square. Let's call this, I don't know, threshold. There we are. Threshold. Okay, so this is, again, it's just a function. What's it going to do? Okay, so it should be a function that returns -1 or 1. Okay, and if I go ahead and run that function, well, now I have, all right, as I go ahead and vary my value of my A neurons up here, my B neurons are now nicely, so pretty much static with their activity. Okay, all right, and that's kind of interesting that we found neural connection weights that can cause that variability to go away. And then if I move this slider down here, cool, all right, as I move things around down here, we're outputting -1, so it's doing a good job of representing the function. What if I do this? All right, I'm feeding in -0.03. This is not doing the function that I asked for. Right? The function that I asked for only outputs -1s or 1s, and here it's outputting the. Right? What it's actually gone and done is sort of implemented a smooth version of this function. Instead of this sudden jump at 0, it's making a somewhat more smooth transition between -1 and 1. It's because neurons, this is entirely due to this, the neurons are trying to approximate this function, and this is the best job that it found that it can do. With more neurons, it's going to do a better job. All right, if I do with, say, 1,000 neurons, all right, then we should see a much faster transition from -1 to 1. In general, with an infinite number of neurons, or with sufficiently large number of neurons, you can always get any function to whatever degree of accuracy you want. The number might be very big. You will also notice there's a kind of a neat thing where when I increase the number of neurons, you'll notice I only increase the number of neurons in A. Right? And that's kind of a neat side effect of how we're building these things here, is that we know when we're making this connection weights, there's 2 steps. One of them is, okay, how do we encode the information? That's the encoders for B, but the first step is taking whatever this neural activity in A is and decoding out the value that I want. All right? So when we solve for the connection weights that approximate this function, we're really starting with just the information in group A. Okay? And then once we found those connection weights, now we're multiplying those by the encoders of B in order to find out how B could best encode that information. So that means if I've got a hard function that I really want, that I'm going to need more neurons in order to approximate that function as well as I want, I'm going to need to only increase the number of neurons in A. Okay? Increase the number of neurons in B just increases how well it approximates the answer. That said, lots of times when I've been implementing algorithms, even though I think about the algorithm in terms of, oh, I want a step like this, it often turns out that, you know what, that smooth version of that function, that's totally fine. Right? There's all sorts of reasons why when you're actually implementing an algorithm, really what you want is you want a smooth transition between options, rather than something where if the input is 0.0001, it does one thing, but if the input is -0.0001, then it does something else. Maybe that's not a sort of thing that biology needs to do often. Okay? And if it does, then the claim is we're going to need more neurons to do that. All right, so we can connect neurons and compute functions. And so we've done this example here. There's a neat sort of biological, or a neat sort of difference between these neurally implemented algorithms and computer algorithms we can see already. One is that as far as biology is concerned, all there's connection weights between A and B, right? Whether or not those connection weights compute the identity function, or they compute x squared, or some other function, or sin x, or some really complicated function, doesn't matter to biology. Like, it's still the same numbers of connections, still around the same sort of connection weights, same sort of neural activities, patterns. If you're going to pass information from one place of the brain to another, you can sort of, for free, also do some computation on that. Of course, as long as that computation is a relatively smooth function. If it's a function with big sharp changes, then you might need more neurons. So the two aspects in which biological algorithms are very different from computer science type algorithms. We've just done that. Okay. So that basic idea is there. Let's build up a few more complex situations. Whoops, there we are. Save that. We're going to go to example 4. All right, so let's say I want to add two numbers together. Okay. So I'm going to say, all right, there's stim A, that's A, stim B, 0. Let's go ahead and delete all that. And we're going to say there's a connection from stim A to A. There's also a connection from stim B to B. This starts being the point where having this graphical interface is handy, because then you actually see what the heck is going on. So, all right, stim A goes to there, stim B goes there, especially if I've like messed up and connected something to the wrong thing. Like if I did a little typo and it's connected stim B to B, then, oh, okay, yes, this is wrong. But if I actually connect it correctly, everything's fine. And then let's say I have another group of neurons C. Ensemble, neurons, 100 neurons, dimensions is 1. Okay, and I want that to be the sum of the two. That turns out to be really easy. I make a connection from A to C, and I make a connection from B to C. Oop. I have to spell connection correctly, though. There we are. And if I do that, so nothing's, I'm solving for connection weights in exactly the same way. I'm plotting things exactly the same way. Nothing has changed from what I was showing before. But now what we should see is that C ends up being, well, if I do 1 plus minus 1, I get 0. Yay. 0.5. Yay. All right. I get the sum of the two. So 0.4, 0.37, I'm getting about 0.77. Okay. So it is successfully adding. Of course, if I do 1 plus 1, I'm going to get a wrong answer. I'm going to get an answer somewhere above 1. That's again because of this radius issue, that this group of neurons is set to have a radius of 1. If I wanted that to be able to handle a larger range of numbers, then I would just adjust its radius. Okay. And set that range minus 2 to 2. And now we can do 1 plus 1. Okay. All right. We can add things. Oh, I guess as an interesting point in there, why don't I just always set the radius to be 10 million so that we just always can handle whatever ranges? Well, you may have noticed that as I increase that radius, so let's go up to radius of 20, we're now all of a sudden noisier. Why are we noisier? Well, we've got the same neural resources and we're spreading them out over a much larger range, or sort of the neurons are sort of tuned for a much wider range. So of course the accuracy is going to drop, and it does exactly what you would expect, that if you multiply by 10 the range of values that it can represent, then your accuracy is going to drop by a factor of 10. So nothing too special there, but it's again just another reason to keep in mind that neurons are going to need to represent things in some range. Okay, but we can just add things. Okay, so anytime you make multiple connections into a group of neurons just with this sort of structure, it just falls out of the math that the represented value is going to be the sum of the two. Right? And you just don't even have to pay attention to it when it's creating these models. All right. But there's other ways I might want to combine information. All right. What if I wanted to have the group of neurons C represent A and B? or not logical and, but I want it to represent the vector a comma b. So what if I want C to be a two-dimensional population that represents both things? That's just all right. If groups of neurons can represent multiple things, there needs to be some way of causing those things to get combined in the first place. Save this. Go on to that example. 5. All right. So how do we do that? Well, let's pull the radius back down to 1. Dimensions. We're saying that we want C to represent both items. So I'm going to say dimensions is 2. Okay, so now C is, now when it generates the neurons in group C, there's neurons that are going to have, that will be sensitive to more than one thing. But now this connection here, now we get an error. And that's because, well, look, A is one thing, C is two things. How are we going to connect those things together? What I really want is I want the value in A to only affect the first value in C. So how can I do that using the tools that we've seen so far? And in particular, when I go ahead and make a connection, I can define an arbitrary function and tell it to go and use that function. So how can I use that to do what I want here? Well, here's a function. We'll call it func A. I don't know. So this is okay. So this is a function. It goes from, so A is one-dimensional, C is two-dimensional. So this X thing is one-dimensional. But this function needs to return two things. And what I could get it to return is that. Right? That's a perfect, whoops. That's a perfectly reasonable function. Right? Return X comma 0. Right? It takes in one dimension, outputs two dimensions, but the first of those outputs is whatever the input is, the second one is always 0. It's a valid function. It's a weird function. Why would anyone want that? Well, consider what happens if I do this. Right. And then I do a similar thing for the other one. Okay, I've now got two different functions going into C. One of them is saying, hey, whatever the value is in A, have that modify the first dimension. And the other one is saying, whatever that value is in B, have that modify the second dimension. And if we have two different inputs to an ensemble, we know from the previous example that C should get the sum of those two things. And so that's exactly what we want here. If I hit play now, C is now two-dimensional. Oh, this graph is, I changed the range of this graph. There we go. All right. If I go and change this one, it changes that value. If I go and change this one, it changes the other value. Right? Where this is a different way of combining information together. Okay? Structurally, as far as the neuron, as strong as neurons and connections goes, there's no difference between this and the addition. All that we're doing is we're using this function stuff and the definitions of the ensemble to change how Nengo is solving for the connection weights in here. Okay? But as far as actual connection weights goes, and as far as the actual underlying simulation goes, it's still just a bunch of spiking neurons with some connection weights. Okay? We're just generating the connection weights in a weird way. Okay? So this group of neurons C is now combining the information from A and B, but it's still representing them as two separate values. Again, it's not like there's, each neuron in C, it's not like half the neurons in C are sensitive to A and half the neurons in C are sensitive to B. If we go ahead and look at the spikes, we can hopefully maybe see that. Each neuron in C, it's sensitive to some combination of A and B. Oops. Here we are. All right. So so C is still doing a distributed representation of those two values, but we're now just able to build that up. This sort of function definition and sort of putting values in certain dimensions, math-wise, this thing that I've just described here is exactly what's going on here, and it's just sort of, okay, this is a weird way of doing functions, but we can do that. Because this looks a little bit ugly and is sometimes a little hard to read and it's hard to interpret, I like sort of introducing that as the basic idea, but then we also added some special syntax to Nengo to just sort of do that automatically for you in a way that's maybe a little bit more readable. So the way we do that is we can say connection from A to C0 and a connection from B to C1. Okay, and then we're going to get rid of this stuff. So these two lines down here, those are identical to what we defined up here. Okay. What we're doing here is we're using this square bracket syntax. That's Python notation for, like, if you have an array and you want to refer to an element in the array. And Python is one of these languages that starts counting at 0. So C0 is the first dimension that is represented inside C, and C1 is the second dimension represented inside C, and so that's just a shortcut for defining those connections. But I just want to show that other way. I mean, it's under the hood, it is still doing this same code that we're showing up here. I mean, it's still finding connection weight matrices that decode a function like that to go ahead and connect. Okay, this bottom thing is a little bit easier to type and read. All right, we can combine information together. So we showed how to add. I have two numbers, I want to add them. I have two numbers, I can now represent both of them. What if I have two numbers and I want to multiply them together? That seems like sort of the simplest thing to do. How can I do that? Just using the components we've seen so far. That's a little tricky, right? So if I try to think of this as the same way, so if we have C, so the A is one-dimensional, B is one-dimensional, C is one-dimensional, and then I sort of say, okay, I want to define a function. I've got two different connections here, but I want these connections together to do something like multiply. So they're like, just with the syntax that I presented here, it seems like there's no good way to do that. No, like how I can't write two different, how if I have two different connections, one from A to C and one from B to C. Let me start this example as example 6. If I have two different connections, one from A to C and one from B to C, and I want together to be the product of the two going in there, how can I even define that to happen? Right? Like what functions could I possibly define here that would make the product, or make A times B show up in C? And there's a reason that the syntax doesn't support that, because it turns out that if you try to do that optimization, if you try to do the optimization across all of these connections into C, where if you have A and B represented as two different groups of neurons, it turns out there is no good way of approximating a function like multiplication. Okay. Won't go too far into the details of that. It is a variant of the XOR problem in traditional neural networks. It's just, and in traditional neural networks, the solution is, oh, okay, you add in hidden layers, and that will let you compute whatever function you want. We're going to do exactly the same trick here. If I want to have A times B represented somewhere, okay, what I'm going to do is I'm going to make C say, all right, be two-dimensional. So C is two-dimensional. And then I'm going to have another group of neurons, D, which is one-dimensional, and that's where my answer is actually going to go. Okay. I'm going to do a connection from A to C0, and a connection from B to C1. So that's the same thing that I showed in the, oops, except I have to spell connection correctly. That's the same thing that I showed with the combining information together. And now when I do this one, now I can do, say, product x, return x, 0 times x1, and go connection from C to D with the function being the product. Whoops, product. Okay. So this is two things. One of the things is just showing you how you can do something like computing the product of if I have information in two different groups of neurons. Whoops, it helps if I actually pull up a graph for D. Right. So if I do this, all right, multiplying anything by 0 doesn't seem to do anything. Put this up at 1. Now I go vary this one. Oh, cool. Yeah, multiplying by 1. And here, multiply by minus 1. All right, seems to do things. Why is it not, why if I do 1 times 1, why am I getting too small a value? It's the radius thing again. So I'm going to go ahead and increase that radius. So now I should be able to do 1 times 1. Now I get a 1 out. We're multiplying by 1. That's all good. It goes down to minus 1. Multiply by minus 1. Set this to 0. And now we're multiplying by 0. Okay, so it's doing what we want. So it's one thing. So okay, cool. I can get neurons to do this. We're also making an interesting biological claim here. We're also saying, hey, look, if you have a neural algorithm that requires a nonlinear function of two variables, then you're going to have a group of neurons that encodes both of those pieces of information. It's not a particularly profound statement. That's certainly that's a variant of the XOR problem. It's an old idea in neural networks that you need something like that. And certainly you can start, and some of the things we've done in Nengo that we'll get into later in the course is that there's the possibility of, as you go with more complex neuron models, you can start doing more complex things without requiring this hidden layer of neurons. But with a lot of, that ends up being very constrained. There's only certain sorts of functions you can do like that. In general, if you want to do these sorts of nonlinear algorithms, having these intermediate variables seems to be pretty required, and it seems to be pretty consistent with biology, or at least lots of situations. Okay. Cool. We can build up complex algorithms. We can represent variables. We can compute functions on those variables. We can do, combine them together. We can add things. That looks like a pretty complicated system. And so that's going to be the basis for doing all the neural computation in this course. A couple good proofs. Yes, with enough neurons, you can approximate any function to any degree of accuracy. The mean squared error seems to be, inversely proportional to the number of neurons. Of course, that's dependent on the exact neuron properties and the distribution of tuning curves. But we can also sort of say things like, well, what functions are these neurons good at approximating? I sort of hinted at that when I was showing, oh, hey, look, they did a good job of x squared, didn't do a great job of that threshold function, where if left than 0, then it should be minus 1. If the input's greater than 0, it should be plus 1. We ended up with sort of a smoothed version of that. So what classes of functions are neurons good at approximating? Turns out that's a solvable question. It turns out that all you have to do is take your tuning curves, these randomly generated tuning curves, or these or the tuning curves that you set based on biology, and do singular value decomposition on them. Right? So mathematical technique that basically tells you what functions are you good at approximating with these curves if you're able to do weighted sums of them. That's really what singular value decomposition is finding for you. And it sort of gives you an order of what things the neurons are good at computing. The best thing that neurons are good at computing is this blue line down here. So that's a function that basically doesn't change much no matter what the input is. If you want a group of neurons to just output a constant no matter what their inputs are, cool, neurons are really good at that. The next thing, I mean, that's pretty useless, but neurons are really good at it. The next thing that neurons are really good at is this green line. And so that's a function that just linearly changes based on its input. Right? So neurons are really good at computing linear functions. The second best thing that they're good at is this, so the next best thing they're good at is this red line, and that's x squared. All right. And the next best thing is x cubed, x to the fourth. Technically, it turns out to be the Legendre basis, so it's some scaled and weighted versions of polynomials, but that is what directly falls out of this sort of tuning curve, which is a pretty common tuning curve to find in the brain. Neurons are good at computing functions that are well approximated by low-degree polynomials. That's kind of cool. All right, that starts making a strong claim about what sorts of steps you should see in the algorithms that you're trying to implement if you're trying to constrain yourself to think about algorithms that neurons would be good at implementing. I will put on a big caveat there that this depends so much on what the neuron model is. And yes, as you get in more complex neuron models, this is going to change slightly. And that's an ongoing line of research that we're looking at is, how does this change in different situations? Right now, there's relatively few situations where this changes. There's a couple cases where we can make it be much better at a threshold function, but overall, in general, this is still a pretty strong statement across a pretty wide range of neuron models. Okay, and I would love to find situations where, like, oh, this particular neuron model would be really good at this class of functions, because then that makes a really strong claim that if I come up with an algorithm where I'm like, oh, hey, this is an algorithm that I really think matches human behavior, then that would be a really strong claim of saying, ooh, and then I should also be able to find this sort of neuron in the part of the brain that does that. So that's sort of a thing that I'm actively looking for. Cool. All right. So where to summarize all of this so far? What do neural algorithms look like? Well, fine. If I'm trying to come up with algorithms that fit well with this sort of understanding of what biological neural algorithms should be, then what do these algorithms look like? Well, they should be something. There should be a whole bunch of vectors. So we know groups of neurons can represent vectors. Connections between groups of neurons compute functions on those vectors. I haven't highlighted it too much right now, but when we compute those functions, we're also applying a filter on those. So that low-pass filter, that synapse model, the thing that's turning spikes into some sort of release of neurotransmitter and decaying, that is also happening in there. We're going to talk about that a little bit more in the next lecture. Actually, it's going to be the foundation of everything in the next lecture. So there's something about the synapse that is going to introduce some sort of temporal filter, but the main thing that we're talking about here is that the actual function being computed when we make connections between groups of neurons, if I go ahead and change what those connection weights are, we're going to compute different functions. To a certain degree, this is kind of like standard connectionism. I still have components and connections between them, but there's an interesting difference. So one way to think about what we're doing here is in standard connectionism, there's often this idea of, all right, you've defined these nodes and you have things called neurons, but people are sort of using the sigmoid curves or some sort of non-spiking neuron model there. And if you really press them on what the biological mapping is, they'll say something like, oh, okay, well, this one neuron in my model that really maps onto like the average of activity of 100 neurons or something like that. Okay. And then they're connecting these neurons in their model with connection weights to do different things. Okay, So if we take that metaphor seriously, then actually what we're doing here is we're doing something slightly more powerful than standard connectionism. In standard connectionism, you have these nodes which represent values, and even though they're called neurons, they're often sort of imagined to be the average activity of a large number of neurons. But if we actually take the step that we've started describing here and say, okay, no, these are neurons, but we don't average their activity. All those neurons, there's some heterogeneity in here. Those neurons have different properties. Those neurons all have slightly different tuning curves. And when we make connection weights from those, we don't have to just have one number doing the same connection weight to all of those neurons. If we instead do this step that I just described here of, hey, go ahead and find a optimal connection weights to compute some function. Now all of a sudden we're doing sort of something like normal connectionism, but whenever I make a connection, I don't get to just specify a weight. I can also specify a function to compute. Okay, some functions going to be easier than others. And it's going to be based on how smooth the function is and what those tuning curves are, what that variability is of the neuron properties. And sometimes, what functions are easy and what functions are hard is not all that intuitive. So for instance, the function find the maximum of A and B turns out to be a really hard function to approximate. It's not a particularly smooth function. Whereas the function sine A plus B times cos B minus A, it's complicated to write out, but that is going to turn out to be a nice and smooth function. So what's a hard function and what's an easy function is not going to be all that obvious. Okay, and might conflict with our intuitions from normal computer algorithms. All right, so that's kind of cool. That lets us go ahead and build things. Where are we going to go from here? Well, the next big step is going to be, what the heck are we going to do with recurrent connections? And what happens if we just take what we've shown so far and use it to build recurrent connections? Because there's a lot of places in the brain that do recurrent connections. What's going to happen to our system when we do that? That'll be the topic of the next lecture. And that's going to be the one that's, I think, going to give us a fundamentally new thing that we can do with these neurons. Everything that I've shown so far, fine, I can get neurons to approximate functions. I'm doing it kind of a weird way, but it's not that fundamentally different from normal neural networks. But we're going to use, I'm using really weird notation to do all that, and showing that it works in spiking neurons, fine. But the point of the next lecture is going to be, let's take all this frame that we've done right now, apply it to recurrent connections, and that's going to give us a new type of computation that we can do. So I hope you'll come back for that, and thank you very much.